Good morning and welcome to another edition of Kung Fu Physics, where we are currently making our way through the physics GRE problems one at a time. And today's problem is off of the 2001 Practice Physics GRE exam. It's number 89. It looks something like this. If you have it, go ahead and flip to that one so you can follow along with it in front of you. Again, number 89 off of the 2001 exam. It's a mechanics problem, very fairly straightforward. It's regarding angular momentum. I would say conservation of angular momentum is the way to solve the problem. And there are a couple ways you can screw it up, but otherwise it is pretty straightforward. So let's hack right into it. Looking at the answers briefly, it's an angular velocity that will be our answer, but those answers are all too close at this point to say anything much interesting about them. In order to solve the problem, I'm going to have to carefully get the right answer and pick it rather than trying to eliminate wrong answers. So dive right into the problem. Quick read through number 89. A child is standing on the edge of a merry-go-round that has the shape of a solid disc as shown in this figure above. The mass of the child is 40 kilograms. The merry-go-round has a mass of 200 kilograms and a radius of 2.5 meters and is rotating with an angular velocity of omega equals 2 radians per second. The child then walks slowly towards the center of the merry-go-round. What will be the final angular velocity of the merry-go-round when the child reaches the center? The size of the child can be neglected. Okay, so conceptually, what's happening here? You have this thing is rotating around and somebody is going to move, changing the moment of inertia. Will the angular rotation change? Conceptually, hopefully you can envision in your head how yes, if the moment of inertia is going to change, certainly the angular rotation must change. And if just you can't see that in your head, then certainly just looking at the first equation that I would be using for this problem anyways, which is just setting the initial angular momentum equal to the final angular momentum. If this is changing, and so this is different than this, certainly this has to be different from this as well in order for this equation to hold. And so yes, the omega is going to be different. That being said, if we were quick and clever and we want to eliminate answer A, we could, because answer A is 2 rads per second, which is what the initial omega is. And so conceptually in our head, we are going to realize that the omega is increasing. It's going to be rotating faster as the kid walks from the outside to the inside, and we can knock out A because it's not going to stay the same. So let's go ahead and get started, and I'll fill you in on the one hang-up, well, a couple of hang-ups when I did this problem on the first couple takes that I wanted to retake and give you a better idea and not sort of muddle things up. So we start plugging in what we need here specific to this problem. So what is the initial moment of inertia? We use the moment of inertia of the disc, and then because the kid is on the outside, it's going to be we're going to have to add that in via the parallel axis theorem. The moment of inertia of a disc, if you don't recall it right off your head, I know I didn't. I wanted to, and I'll double check anyways if I actually have it available to me, but these are the moments of inertia that are available on the physics GRE. And so I see disc there, the second one down, 1/2 mr squared. That's what I want to use for the moment of inertia of the disc. I want to add in the moment of inertia caused by the child out at radius r, because she's out at the edge. And so that's just going to be little m, that's the mass of the child, times r squared, times my initial rotational velocity. The final, now this is where I got screwed up. Imagine after the kid has walked into the center. What is my final moment of inertia going to be? Well, I'll still have the disk there. 1/2 m. And this is where I paused. I said, oh, is it just going to be the mass of the disk, or do I have to do big M plus little m? Do I have to add in the mass of the child? And as it turns out, that's a mistake to add in the mass of the child. That will get you off course, and by the end, you'll end up with an answer that's not present there, and then you'll have to be going back, and if you're sharp, I guess maybe you could correct yourself with that. But I want to talk real briefly about why that is the case. Why is it that when the child walks in towards the center and is standing smack dab in the center of the merry-go-round, why is she not affecting the rotational inertia of this system at all? Not even by her mass. Well, the reason is that little parenthetical that you would almost be tempted to forget about reading when you're in a hurry to read this problem. But it says the size of the child can be neglected. So the size of the child can be neglected. It is a point mass sitting directly at the center of the merry-go-round, and it has zero. It contributes zero to the rotational energy, or the moment of inertia of that system. I should say contributes zero to the moment of inertia of that system. And it's counterintuitive. It's not realistic in any physical model. You would have to take that kid and model them as like a cylinder, because there's no person whose size is negligible. But given those constraints and given that description, you actually are forced to realize that even though the kid has mass, the mass is not affecting the rotation at all, because it's a point mass directly at the center in this theoretically type problem, and you do away with it. You don't need it. It's very counterintuitive. I don't like that part about the problem. I'll be honest. I think that's a little cheap, and it is confusing. But that being said, that's the way you do the problem, is you just do the mass of the disk, and then that's times the omega final. So quickly, I would be plugging in numbers here at this point. 1/2, I think big M is 200. I'm going to leave r squared in. And at this point, if I was actually doing the exam, I would probably be substituting it in because I've done this problem already before I make this video. I know that it's going to cancel out, but yeah. If you're quick, if you're sharp, you could look and see the r squared is in all the terms. It will cancel out. Omega f is what we're trying to solve. As I said, the r squared is in, well, I'll do one more step. And then, so this is going to be 200 r squared. Sorry, let me put in the 40 there. Plus 80 squared plus 100 r squared omega f. And here it's blatantly obvious that you can just toss the 2.5 meters, because we don't want to square 2.5, do we? No. No, we don't want to if we don't have to. And that's where the answer pops up pretty readily. I did mess up some of my algebra, and so in a previous take, I mean, when I did this, I forgot to carry the 2 through. And so if you're a little sloppy with algebra sometimes, like I am, by all means do the extra step. Be careful, be accurate. Accuracy and getting to that right answer is more important than the extra moment that's going to take you by throwing on some parentheses and making sure you distribute through your algebra. I mean, that's a terrible shame to mess up a problem by just screwing up the algebra. So be careful with that when you're doing these problems. And that gets you to your final omega, which is 2.8, and that is one of our answers, answer E. And so that's how we are going to answer the problem. And that's that for that problem. A couple of little tricks in there and a couple of little things that you might not have thought about before. So that's all. Study hard. See you next time.